Hello everybody, so I've given you some time to look at this Larson illustration and I just want you to become aware of some of these terms: dissolving, soluble, insoluble, and polar, okay? These are terms that are going to come into play in this presentation of crystallization. So hopefully you got the joke. So crystallization is a purification technique. So you'll remember from melting point was used to establish purity, but crystallization is actually used to purify. So we're looking to try to make crude solids pure with this technique. So I always like to pull in some real world example before we jump into the laboratory technique. I want you to think about crystals, and maybe you have some connection to crystals, maybe you have no connection to crystals, but I want you to think about crystals that you know about or that you don't know about. Here we have the Nika cave in Mexico, and these crystals, as you can see, are so large that they're bigger than a human body, and these crystals have been growing underneath the ground around 26,000 feet below the ground. And it's very hot under there. It's around 140 degrees Fahrenheit, around 55 degrees Celsius. So when geologists go to study these crystals, they have to wear special thermal suits. They have to wear headlamps because it's completely dark. So another interesting thing is, because I work with microbes, there are microbes that live in this environment too, extremophiles that can live among these selenite crystals. Okay, so these are non-organic crystals, but even still, they're very interesting to me. They catch my eye. So I thought you would like to see these. So keep in mind, just imagine how hot it is down there wearing this suit. You can only stay down there for about 20 minutes at a time. Imagine getting down almost 3,000 feet and then having to come back up to the surface because you can't tolerate the heat anymore. So think about that. And let's think about crystals. Crystallization, okay? So the purpose of the crystallization experiment is to teach you about this technique that is used to clean up dirty solids in the organic chemistry laboratory, okay? So it involves two things. It involves the removal of insoluble impurities like sand or paper, things that can't dissolve in a liquid. And then the removal of soluble impurities, those things that can dissolve in a liquid, okay? So we're gonna take a solid and we're going to use a solvent or a liquid to help to purify that solid, okay? This is very useful for organic chemical synthesis. Imagine that you've synthesized a chemical, you've conducted a chemical reaction, there's leftover starting materials, or there's byproducts there that are actually causing impurities in your final product, so you will employ this technique of crystallization to clean up that product that you made. So let's take a look at two different phenomena. We have crystallization. On the right, you can see these crystals, they're very fine, pointy, needle-like shape. I told you in the melting point presentation, when we talked about crystals, the shape of the crystal, the more needle-like or the more geometric it looks, it's more pure. Okay, so crystallization, it happens from slow and selective crystal growth, okay, and that results in a very pure material. So imagine molecule by molecule, they're attaching to each other and forming this crystal lattice, okay? It's slow and selective. We want this geometry to result, so impurities, we don't want them to get involved in that crystal lattice, and this happens by being very slow growing. Now, precipitation, on the other hand, what we see on the left side, is a solid sort of crashing out of solution. It's usually the result of a chemical reaction, and the process is very rapid and non-selective. So imagine all of these molecules are coming together and they're just crashing out of solution. It results in a very impure material, and typically when you have a crude solid that has come out as a result of precipitation, it also has a very dull look to it. It doesn't look crystalline, it looks chunky and muddy, okay? So look at the difference, first of all, between these two ideas. So crystallization is slow, selective, results in pure material. So this is what we want to achieve when we're trying to clean up a dirty solid. And precipitation happens so quickly that it's non-selective, and it usually results in a mixture of material that has impurities in it. So what's the objective of this experiment? It's to purify a dirty unknown via crystallization from water. So I mentioned you'll take a solid, you'll involve some sort of solvent or liquid, and in this case of this experiment, it is water. Okay, so the unknown dirty compound that you would be issued could be benzoic acid, salicylic acid, or sorbic acid. And you can see the structures of each one of those down below. So you'll notice that all of them have a carboxy group on them. Here, oops. Go back there. All of them have a carboxy group on them, and some of them have double bonds, some of them have an extra hydroxy group. Okay, so I want you to think back about, that I mentioned in the melting point lecture, about structure and how, depending on the intermolecular forces that exist inside the molecule, it's going to require more or less energy to actually get that material to melt, to convert from a solid to a liquid. So just on your own, look at the structures of these and understand why the melting point is higher for salicylic acid versus benzoic acid, for example. And I'll give you a second to think about that, but if you notice, salicylic acid has an additional hydroxy group on it, which means more hydrogen bonding can go on. So it's going to result in needing more energy to break up those intermolecular forces of hydrogen bonding to make the salicylic acid melt. So it's really good for you to keep drawing parallels among all the labs that you're doing. Like, go back and think about the lab that you just did and how it can continue to correspond to other experiments you'll do in the future. And so the second part of this experiment is to now identify the unknown by measuring the melting point and then doing mixed melting point analysis. So after you take one of these impure unknowns, again, you won't know which one you have, you'll do the crystallization to purify it, and then you'll take the melting point, and then you can figure out which unknown you have. And to confirm that, mixed melting point will be conducted. So what is the idea of crystallization? Well, we have to talk about solubility. So remember from that comic, there was a mention of insoluble. So it says here that the first problem in performing crystallization is to select a solvent for the material to be crystallized, showing desired solubility behavior. So you have to understand what's going on when you're doing crystallization. What you're doing is you're taking a solid and you're adding a liquid to it, and you're trying to get that solid to dissolve. But temperature needs to come into play, because think about this. You want to try to reclaim that solid from the liquid. So you want to look at these 3 general solubility behaviors, and then you can understand a little bit more about what I'm getting at. So there's 3 different solubility behaviors. And remember, to be soluble means to dissolve, okay? So the first one is the compound has a high solubility in both hot and cold solvent. The second behavior is the compound has low solubility in both hot and cold solvent. Now, the third behavior is the compound has a high solubility in hot solvent and a low solubility in cold solvent. Okay, so what is this saying here? Imagine you have hot water and cold water, and you have this solid material, this unknown solid. If it's if it's highly soluble in both hot and cold solvent, what does that mean? Can we reclaim it from the solvent once the solvent cools down? No, we cannot, because it will dissolve when it's hot, it will dissolve when it's cold, and now we can't reclaim it. We can't get the solid back. But what about the compound doesn't dissolve in either hot or cold water? Then we're not going to purify it. The best behavior is characteristic number 3, where the compound is soluble in hot solvent and not soluble in cold solvent. So this is very crucial, because imagine you dissolve this dirty solid in a hot liquid, And then as that liquid cools down, the solid is going to slowly come out of solution as crystals and pure. This is what we're trying to achieve, okay? So solvents showing the first two behaviors are not useful. Solvents displaying the third behavior are ideal, okay? So keep that in mind. We want it to be highly soluble in hot solvent and not soluble or low solubility in the cold solvent because we want it to come back out of solution so we can actually isolate it. So here is a graphic showing those three behaviors, okay? So if we look at the y-axis is how many grams of solid are soluble in this solvent, whatever solvent we're talking about, and the x-axis is increasing temperature. So you can see for A, good solvent, okay? So this is the best situation where our solid, notice as we start to increase the temperature, more of the solid material goes into solution. But B, notice that as we increase the temperature, the solid just doesn't go into solution at all. And C, as we increase the temperature, it goes into solution, but also at low temperature, it's very highly in solution. So A is the best, okay? Again, I'll reiterate, we want our solid to be soluble at high temperature liquid and not soluble at low temperature liquid, okay? So again, the ideal recrystallization solvent should dissolve all of the compound when the solvent is hot or boiling, okay? So it should dissolve the minimum amount of compound when the solvent is at room temperature, so that would be considered cool. And it should have different solubilities for the compound and the impurities. That's the most important part. So when you have your unknown solid, we want the solid and the impurities to go into solution at high temperature. But as it cools down, we want the solid to come out of solution, but the impurities stay in solution, okay? Now, another important point is that the solvent should have a lower boiling point than the melting point of the compound. This is very, very important. Why is this? Think about this for a couple minutes. Why would we want the solid to be dissolved in a solvent with a lower boiling point than the solid's melting point? What would happen if the solvent had a higher boiling point than the melting point of the solid? So what would happen? Imagine you're heating up this solvent, has a super high boiling point, higher than the melting point. You reach the melting point of the solid that's in the liquid, and the solid starts to melt. And then it will be really difficult because now you have two liquids, one liquid suspended in another. Very difficult to try to get that solid back. Okay, so this is a very important point. So you see there's all of these requirements for the ideal recrystallization solvent. Another thing is that the solvent should be non-toxic. Why? Because you're working with this chemical and you don't want to get contaminated. And it should be non-reactive. This is extremely important. We want to be using solvents that are inert, that don't react with the solid we're trying to purify. If they react, they're going to change the composition of the solid. And lastly, the solvent should be easily removed from the purified compound. Okay, so we can separate the solid from the solvent via filtration. But if it can't be removed this way, it's going to be very difficult to work with. So there's a lot of factors that play into this recrystallization solvent. Now you'll notice that we're using the term crystallization and recrystallization interchangeably because they're synonymous with each other. So please explain this phenomenon. Benzyl alcohol with a boiling point of 205 Celsius was selected by a student as a solvent to crystallize fluorinol, which has a melting point that is lower than benzyl alcohol, 153 to 154 Celsius, because the solubility characteristics of this solvent are appropriate. So, however, the solvent's not a good choice. So the idea was fluorinol will dissolve in hot benzyl alcohol, but not cold benzyl alcohol, so that's great. But why is this solvent not a good choice? So this touches upon the point that I mentioned to you before. Fluoronol is going to melt. We need to get benzyl alcohol really hot before we can add fluoronol to it. So if we do, it's going to melt right away in the hot benzyl alcohol. This is why this is no good. No good, okay? So remember, if the boiling point of the solvent is too high, it's going to cause the solid to melt. Not a good situation. How are we going to get the solid back? It's going to be such a pain. This is a concept called oiling out. Oiling out is not helpful for us at all. And the second thing is, it's not mentioned in this slide, but the second thing is, remember, we do not want our solvent, in this case benzyl alcohol, we do not want it to be reactive with the solid. In this case, benzyl alcohol is not going to react with fluoronol. But keep in mind that something like, let's say that we wanted to use a base to purify an acid. Not going to work because acid and base will react together, okay? So we'll break for that first part of the lecture and then we'll get started with the next presentation.